I will tell you something about the context of our work, which is a bit different from what you've seen until now. I'll tell you about the problem definition, the adopted technical solutions we've chosen, a bit of prototype development history, our actual prototype that we've been doing tests with, the results we have obtained with this prototype, to finish with a conclusion, near future improvements, tests, and further outlook. About the context. My background is in microtechnologies and applied plasma physics, where I've been doing research. And for the last 10 years, I've been working as a high school science teacher. So the context of this 3D printer, it's a STEM R&D project that has happened in high school. I had 3 high school students that have been working on this, and I had the opportunity to coach them for 2 hours a week at school, and they've been spending numerous hours at home in their garage to make things happen. As you can imagine, for high schools, we had a very, very limited budget, but the good news in the end is it did finally work. So as I said before, the project started in 2016. You've heard enough about advantages of 3D printing and disadvantages of actual construction technology. So that was the basic motivation. And in order to get started, because we started from scratch, we let ourselves inspire with commercial 3D FDM printers using plastic as a print material. One of the main goals was to overcome print volume limitations, referring to the threaded rods that are very common solutions used for those printers. We would have then to adapt such a system to use concrete as a printing material. And also, inspired by these printers, we were convinced that having a continuous pulsation-free material flow would be an asset for having a quality print. And also thinking about sustainability and maintenance of such a system, trying to have a long-lasting, easily cleanable printing material pumping system. As I said before, my background is not in science materials, so this was rather proof of concept on the technological side, and the print materials study and selection will be something we'll have to address in a second step. So, the technical solutions we've chosen were a modular structure that could be scaled up or down with such a system, so you just would have to replace different elements, for example, the vertical elements to have higher print dimensions. We would opt for belt-driven X and Y axis, and for having easy scalability on the Z axis, which shows a belt cable winch system. Actually, we used shutter belts for the prototype we have been developing. For the rest, well, we also opted for adjustable feet so that the print structure could be used in situ, thinking about a surface 3D scan that could be integrated into the printed model. For the pump, we finally chose a peristaltic pump, where you have small illustration animation to have this continuous pulsation-free flow for our print material. And as I started before, we started from scratch. My students did most of the work. To have a wooden frame, basically checking that the winches on the Z-axis would work. After that, we moved on to working model with electronics and motors. We would use steel profiles for the frame. And as you can see on this picture, would have one stepper motor for x-axis displacement, two motors, one here and one on the other side for y-axis displacement, and the four stepper motors for z-axis displacement with cable winches. As already mentioned yesterday, a solution of choice may be an Arduino with the GRBL software, which is openly available. And after setting this up, the first problem we ran into was that the steel frame was simply too heavy. So we then came to prototype 3, which is the actual one. It was all redone using aluminum profiles. We kept the motors. We added the pump. The peristaltic pump uses a silicon pipe with inner-outer diameters as given here. And we had a printable volume of 300 times 200 times 200 millimeter cube. For the printing material, we were advised from someone from the University of Luxembourg who's into material science to use Dijkhoff the ultra-high performance concrete for testing. And as it turns out, we had a first version without an extruder, so just using the silicon pipe as a nozzle, and a second version where we have added an extruder and also a small modification of taking away the electronics for portability. So, we have done tests, and we were able to print structures, simple, with rectangular footprints, with the dimension shown here. We have tested different water-cement ratios, and we reached the best results with ratio 3:1. We estimated for this print our pumping debit to about 100 grams per minute. And the structures we were able to obtain have the dimensions that are shown here. In this example, we did not use fiber loading nor extruder. And the reason for this is, that what was fiberglass loading, we just had clogging of our pipe, which is rather logic. We tried it nonetheless, and for the rest, we had best results with the water-cement ratio I mentioned before, and quite quickly, with using a little less water, we would not be able to pump the print material anymore. We also did some testing on the ratio between interlayer distance, so z-axis stepping, and nozzle diameter, and the best results were obtained for ratios from 1 to 1.2. Based on the experiments, the tests we've run, we will try to step up to a larger pipe diameter and accordingly use a bigger pump. We've been working on an extruder that we will have to use into tests, especially when thinking about using fiber-loaded print material. And in further future, we also think about using alternative sustainable materials like cob or clay, where we have heard about yesterday. And as loading materials are either fiberglass or also natural material like miscanthus. So that's our project where we have been working on. So if someone has questions about it, just feel free.